Hey everybody, welcome back to Mr. A's Geometry course. Today we're going over the last lesson of Unit 4, which is all about a new type of transformation called dilations. Let's get into it. A dilation is not a rigid transformation. It is not going to result in a congruent figure. Instead, a dilation is called a similarity transformation, which is going to be a change that increases or decreases the length of the sides of a figure at the same rate, right? So when we're talking about rate, for this as an example, you can see side AB has doubled in size, gone from 4 to 8, and all the other corresponding sides also doubled. 3 became 6, 5 became 10. So your sides will increase or decrease all at the same rate. However, the angle measure is going to be preserved when we dilate. So we're gonna have the same shape, just different sizes, like these, right? These are known as dilations. The thing that determines that rate of change for our figures is called the scale factor. We use the letter K to represent our scale factor. And again, that K is going to determine if the shape gets bigger or smaller. Here's some examples of a scale factor. Like our triangles before, we can see the corresponding sides on these triangles have doubled in size from left to right. So the scale factor is 2. These sides grew by double the amount, or we could say we multiplied these values by 2. Direction matters here though. If we're saying like this is the original figure and this is the new one, the scale factor here would be a half because these sides are half the size of these sides. Getting into more precise terminology here, we're not going to say that our shapes grew or shrunk or got bigger or got smaller. Instead, we're going to use terms like enlargement. So an enlargement is a dilation with a scale factor that is greater than 1, and obviously that's going to result in a larger figure. All right, so here's an example of that. Our pre-image is triangle PRQ, and it becomes a larger triangle PRQ. That is an enlargement. So a reduction then is the precise terminology for when our shape gets smaller, and that's going to be when the scale factor is greater than 1, or sorry, greater than 0, but less than 1. Right, so essentially a scale factor less than 1, fractions that are less than 1, right, are going to be reductions that are going to result in a smaller figure. Right, so as we zoom in here, we see our pre-image is that larger quadrilateral that becomes a smaller quadrilateral. That is a reduction. Again, that's a scale factor less than 1, greater than 0. We need to know about these things called the center of dilation when we're performing dilations, right? If you notice our previous examples that we looked at, not only did a shape enlarge or reduce, it also moved positions on the graph. So it didn't just sit still and get bigger or smaller. It actually moved further away from a focused point. So instead of thinking of dilations as just growing or shrinking, we're also moving our points further away from a center of dilation or closer to a center of dilation. A good way to think of this is if I have a scale factor of 2, not only are my side lengths going to double in size, but my points are actually going to move twice the distance away from a center of dilation, right? And that's essentially what is explained here. In our first few examples here, our center of dilation is going to be the origin at 0, 0, right? And if it doesn't tell you, then we're going to assume through our notes here that the origin is going to be our center of dilation. We have here a scale factor of 2, which means we're going to have an enlargement. Our pre-image, that segment CD, is going to get larger on our graph. And I first want to explain how the function notation for this kind of dilation will work. All right, so remember, function notation looks like this. We start with any random point, and it transforms into a new point. When we dilate, all we're really doing is multiplying by the scale factor that's given to us. So we would take the x-coordinate and y-coordinate and multiply it by whatever that value is. In this case, it's 2. So xy would become 2x, 2y, multiplying both the x-coordinate and the y-coordinate by 2. So we can perform this dilation by just using that rule. My pre-image point C was located at 1, 2. C prime then, we would find the coordinates by just multiplying these by 2. So the 1 gets multiplied by 2, gives me 2. That y coordinate gets multiplied by 2, 2 times 2 gives me 4. So my C prime is located at positive 2, positive 4, right there. Do the same thing for point D. My pre-image, D is located at positive 1, negative 1. If I multiply both of those by my scale factor of 2, I will get my image for D prime. 1 times 2 gives me positive 2. Negative 1 times positive 2 gives me negative 2. D prime's at positive 2, negative 2. Right, so function notation is really the key here as we perform dilations. Well, notice this, right? A good way to know that you've done your dilation correctly on a graph is that you should be able to connect your image to the center of your dilation, and your points on your pre-image should be on that segment. So if I draw a straight segment from C prime to the origin, notice that point C on my pre-image is on that line. Same thing, D prime back to my origin, and we notice that point D is on that segment there. This will happen for all dilations. Next up, we are going to be performing a reduction. I know this is going to be a reduction because my scale factor is less than 1 but greater than 0. Scale factor of 1/4 essentially means I'm going to have an image here that is 1/4 the size of my pre-image. And we can perform this the same way by multiplying by the scale factor. So my xy on my pre-image will become 1/4 x, 1/4 y. Multiplying both the x and y coordinates by 1/4. All right, I don't have points labeled here. I'm going to go ahead and just label them A, B, C, and D just so that we can reference them as we do the work here. So point A on my pre-image was located at positive 4, positive 4. If I multiply those by 1/4, I'll get the coordinates for my image A prime. So 4 times 1/4, remember to multiply by a fraction, you would do times the numerator divided by the denominator. So 4 times 1 divided by 4 is just 1. Y coordinate will result in the same value. So A prime is located at 1, 1, right there. Right, B is located at positive 4, positive 8. And again, we're going to follow that function notation there. We're just multiplying by the scale factor of 1/4. 4 times 1/4 will give us 1. 8 times 1/4, again, that's 8 times 1 divided by 4. That will give you 2. So B prime is at positive 1, positive 2 right here. And we continue. C was at 8, 8. We've already established if we multiply 8 by 1/4, the result's going to be 2. So we're going to get 2, 2 for C prime right there. And then point D is located at positive 8, positive 4. And again, we're multiplying the coordinates by our scale factor of 1/4. 8 times 1/4 gives me positive 2. 4 times 1/4 gives me positive 1. D prime is at 2, 1 right there. And again, if I were to draw segments connecting my pre-image back to the origin, we would notice that our points are all going to be on the same line. B, B prime, and the origin all connected there. The same thing would happen with the A's and the C's and the D's. It would all be on the same line. We must be able to describe dilations as well. We have to be able to recognize again that the pre-image does not have apostrophe, so that makes this our original figure. Our image is clearly larger, so that's our key that we have a dilation that has happened. Our shape has grown or shrunk, it's a dilation. We can even more specifically call this dilation an enlargement because our figure got bigger. That gives us a key piece of information there that we know this scale factor must be more than 1. Okay? And the way that we can now determine what the scale factor is by comparing something from our image over our pre-image. All right, so when we find our scale factor, we want to do image divided by pre-image to determine that scale factor value. For example, when I look at side AB prime on my image, that's countable. Going from positive 6 to positive 15, that is 9 units long. And the corresponding side on my pre-image AB, if I count, that's going from 2 to 5, that's 3 units long. So 9 over 3, and we do want to reduce these scale factors as we get them. That is a scale factor of 3. So this is a dilation, an enlargement, with a scale factor of 3. ABC prime is 3 times larger than ABC. Remember, that also means those points are 3 times further away from the origin than A, B, and C are on our pre-image. That's how you describe a dilation. Next up, we have one of the more trickier things here in Unit 4, which is describing a transformation that we can't see on a graph. Now, obviously, if you have access to graph paper, graphing it will help you get an idea of what kind of transformation happened. If we graph this, we would clearly see that one of these segments is clearly larger than the other segment, which would help us understand that it is a dilation. Even without graphs though, we can narrow it down to the type of transformation by looking at the changes that are involved. If the points are not following the same kind of rule of, for example, if I look at a to a prime in my x coordinates, 2 to 5, that's plus 3. If you notice from b to b prime, that same thing's not happening. I'm not adding 3 from -4 to get to -10. So that rules out a translation. And you can do this and rule out transformations just by looking at the changes in coordinates. Graphing would tell you though that this is a dilation, right? We would clearly get a larger segment. So this is a dilation. And remember, finding the scale factor is just going to be something from the image or something from the pre-image. And for this kind of scenario, I can just take a coordinate to figure this out. For example, my x-coordinate on a prime is +5, so that's something from my image. And I can put that over the corresponding coordinate from my pre-image. The x-coordinate for point A on the pre-image was +2. And that gives me my scale factor. I could keep it as that fraction, 5/2. I could write it as a decimal, 2.5. Either of those would be acceptable. Next, we are going to be learning how to dilate when the center of our dilation is not the origin. All right, so remember, when we perform these dilations, we can think of our points moving a certain distance away from the center of dilation. For example, here, a scale factor of 3 doesn't just mean we get a figure that's 3 times larger. It also means that we get points that are 3 times further away from the center of dilation. All right, so what that means for us in order to perform it on the graph is to just pretend that our center of dilation is the origin. So instead of using the actual coordinates of B and C here, which would be 4, 3 for B and 2, 1 for C, we would use these coordinates as if that point A was translated back to the origin, right? For example, point B is 1 to the right and 1 down from point A. So I can think of B on my pre-image as being located at +1, -1. That's right 1, down 1. If I look at point C, I can see that that is 1 to the left and 3 down from my center of dilation. So I can think of that as -1, -3. Left 1, down 3. And now these values will get multiplied by the scale factor to determine the image of our location. So we're multiplying +1 times 3, which gives me +3. -1 times 3 gives me -3. Same thing for point C. -1 times 3 gives me -3. -3 times 3 gives me -9. And now to graph the dilation, we would take these points and follow those distances away from our center of dilation. So again, pretending that A is the origin. And again, we're treating it like a translation now. We're going to the right 3 and down 3 to graph B prime. All right, so from point A, right 3, down 3, B prime would be located right there. Right, then point C prime, again, this is telling me go left 3, down 3, like a translation. So we would go left 3, down 9. All right, so left 3, down 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that went a little bit off my graph here, but then down here would be C prime. That's how we would graph a dilation when our center of dilation is not the origin, but a different point. We're performing another dilation here while our center is at point C, not the origin. So we're considering how far away our points are from C as we dilate this with a scale factor of 1/2. So this is going to be a reduction. My scale factor is less than 1. My figure is going to get smaller. We can also think of this as all of our points are going to move half the distance back to that center of dilation. Right? So again, imagining that C is the origin at 0, 0, we're trying to figure out how far away point A is from that location. That is 1, 2, count this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 to the right of point C, so we can think of that as being at 10, 0. If you're struggling a little with this concept, let me do this for you. If we're pretending that C is the origin, then that means we're pretending now that this is the y-axis and this is the x-axis. then that point A now would be located here at 10, 0. It's 10 to the right of the origin. All right, once we've determined that, we can multiply by that scale factor of 1/2 to get to A prime. So 10 times 1/2, that's 10 times 1 divided by 2, gets me to 5. And then 0 times 1/2 is just going to be 0. So my image for A prime will be 5 units to the right of that center of dilation. So from point C, 1, 2, 3, 4, 5, that would give us A prime right there, half the distance closer back to point C. All right, same idea to find the location of point B, pretending that C is the origin. We're going 1, 2 to the right, and then 1, 2, 3, 4 down. So we would say that point B is located at 2, -4 if C was the origin. And we're going to, again, take those distances and multiply them by our scale factor. So 2 times 1/2 give me 1. -4 times 1/2 would give me -2. So this tells us that B prime will be 1 to the right and 2 down from that center of dilation. 1 right, 2 down, there's B prime. And here would be our image, ABC prime. Because if C is the origin, we're treating the coordinates as 0. Since it is the center of dilation, its image will also be at the center of dilation. And I should mention that for you here. Again, if C is the origin of 0, 0, if we multiply zeros by the scale factor, they're still going to be at 0, 0, meaning that point is going to stay there at that same spot. This, again, is how we perform dilations when the center is not the origin.